In this video, we'll talk about linear programming problems, which are really just solving feasible sets for linear inequalities in two variables, but with word problems. Unfortunately, many people find word problems quite difficult, but I'm hoping that with this video, we can turn that frown upside down. Let's talk about the steps for solving linear programming problems. First, we need to deconstruct the word problem. So we take the word problem, a paragraph of words, and we're going to break it down into a table that describes the constraints and the objective function. Those are the mathematical formulas that we're looking for within the word problem. Then we'll graph the feasible set, as we did in our last video, with solving for the points of intersection that we find. And finally, we'll take those corner points of our feasible set and we'll plug them into the objective function to find our solution. Usually, what we're trying to do with linear programming problems is find the optimal way to do something, which is either maximizing something or minimizing something. Let's look at a word problem. You want to buy some storage bins for your clothes. Bin A costs $10 per unit, needs 6 feet squared of floor space, and holds 8 items. Bin B costs $20 per unit, needs 8 feet squared of floor space, and holds 12 items. If you have $140 to spend on bins, and your room has no more than 72 feet for bins, how many of each type of bin should you buy in order to maximize the amount of items you can store? First, we want to decode this word problem. What I like to do is use colors to group the things that belong together. Like, for example, I see information about costs. Bin A costs $10 per unit, and if I look on, I can see bin B costs $20 per unit. So I'm going to make a line for cost. I should, before I do that, define some of my variables. So maybe what I'll use is x and y, since we always use x's and y's when we're graphing. So maybe I'll say that the number of bin A's that I buy will be x, and the number of bin B's that I buy will be y. This is what's called defining your variables. So in terms of cost, we've got $10 for every bin A, $20 for every bin B. And if I keep going, I also find another piece of information here about cost. What I can see is that I only have $140 to spend. So I know that in total, my costs need to add up to less than or equal to $140. Let's see what other information we can find. If I keep reading, bin A needs 6 feet squared of floor space. So I've got some info about floor space. If I keep reading, bin B needs 8 feet squared of floor space. And if I read on, my room has no more than 72 feet squared of floor space. So I've got the space issue to deal with. I have 6 feet squared for bin A, 8 feet squared for bin B, and in total I have to stay less than or equal to 72 feet squared. That's all I've got. The last piece of information that I see here is about how much each bin can hold. Bin A holds 8 items, bin B holds 12 items. And if I keep reading, what I find is that the last sentence tells me I'm trying to maximize the amount of items. That keyword maximize tells me that this information about number of items is the thing that I'm trying to optimize. That's my objective function that has to do with number of items. So I've got 8 items for bin A, 12 items for bin B, and this is what I'm trying to maximize. So For the variable I'm trying to maximize, I usually just set it, or I always set it equal to some variable. Let's say V for volume. So we've decoded the word problem. Our next step is to write equations that represent what we've decoded here. So here's our table. From here, it's easy to write down the equations. If we're going for cost, I can write 10x plus 20y needs to be less than or equal to 140. That's actually not an equation, it's an inequality. It's a constraint that tells us that our costs have to be less than 1 or equal to 140. For space, 6x plus 8y needs to be less than or equal to 72. And our objective function says that 8x plus 12y is what we're trying to maximize. This is our volume, and this is what we want to maximize. But there's two hidden constraints in here as well. The non-negativity constraints. If x represents numbers of bin A, then I can't have a negative number for x. It has to be greater than or equal to 0. And if y represents numbers of bin B, then y also has to be greater than or equal to 0. Those non-negativity constraints are usually here with word problems, so we don't want to forget them. Now that we've written out our inequalities and our objective function, our constraints and our objective function, we can go ahead and graph them using the methods from the last video. So we write out our problem in terms of the constraints. We can leave the objective function for now. And we want to graph these. So we're looking for x-intercepts and y-intercepts. So again, let's imagine that we set this as an equality. 6x plus 8y equals 72. Then we can look for the x and y intercepts. So if we look for the x-intercept here, we set y equal to 0, so we're talking about 6x equals 72. Dividing both sides by 6, and we get x equals 12. So we've got our x-intercept at x equals 12. Then we let x equals 0 to solve for y, so 8y equals 72. Dividing both sides by 8, we get y equals 9. There's our y-intercept for this line. Y equals 9 right here. So this line looks like this. Then we have to decide which side to shade. So if I picked 0, 0 as a test point and plugged it in, I'd get 0 plus 0 is less than 72, which is true. So the bottom we keep and the top we throw away. Next line, 10x plus 20y is less than or equal to 140. So let's set y equal to 0. When we set y equal to 0, we get 10x equals 140. Dividing both sides by 10, we get x equals 14. There's our x-intercept at x equals 14. For our y-intercept, we set x equals 0, so we get 20y equals 140. Dividing both sides by 20, and we get, y equals 7, not 70. So there's our y-intercept at y equals 7. And this line looks something like this. If we pick the test point 0, 0 again, 0 plus 0 is definitely less than 140, so that's true again. So we throw away everything that was above the line and keep everything that was below the line. So that's our shaded region now. If we want to include our non-negativity constraints, what this means is that for the top one, we should keep all positive x's and we should eliminate all negative x's, which are everything to the left of the y-axis. If we want to keep y greater than or equal to 0, then that means we want to keep positive y's and eliminate negative y's, which is everything below the x-axis. So what's left for our feasible set is this small area right in here. We're not quite done yet. We need to identify the 4 corner points of this feasible set. 3 of them we can easily read right from the graph. This corner point here was our y-intercept. It's the point 0, 7. This corner point was an x-intercept at 12, 0. This corner point is just the corner point 0, 0. And this corner point, we would need to solve for the point of intersection of the 2 lines here and here, using either substitution or elimination. I've gone ahead and done this beforehand, and that point ends up being the point x is 8 and y is 3. So because my drawing's a little bit messy, it doesn't quite line up with 8 and 3, but that's why it's important to use substitution or elimination to solve for the point of intersection and not just use the graph. So we've got 4 corner points here. 0, 7, 12, 0, 8, 3, and 0, 0. Once we've solved for the corner points of the feasible set, it's our last task to sub those into the objective function that we found at the beginning. Our objective function was 8x plus 12y equals our volume. So let's see what our volume would be at each of these corner points. At the first one, we've got 8 times 0 plus 12 times 7 equals, okay, so 8 times 0 is 0, plus 12 times 7 gives us 84 items that we could store. At our next corner point, we do 8 times our x-coordinate, which is 12, plus 12 times our y-coordinate, which is 0, and we get 8 times 12 is 96, plus 0 gives us 96 items we can store. Third corner point, 8 times the x-coordinate, which is 8, plus 12 times the y-coordinate, which is 3, gives us 8 times 8 is 64, 12 times 3 is 36, so 36 plus 64 for a total of 100 items we could store. 0, 0 here, if we plug it in, we're going to get 8 times 0 plus 12 times 0. So of course, if we don't buy any bins, we're going to get 0 amount of storage space. What we wanted was the maximum amount of items to store. So what we want to do as a solution is we want to buy 8 units of bin A and 3 units of bin B. I hope this video made you feel a little bit more comfortable with linear programming problems. I'll see you in the next video about matrices.